Good evening. In this talk, I will briefly present CP Optimizer, which is a generic optimization engine with a particular focus on solving industrial scheduling problems. We started developing CP Optimizer in 2007. Some years before our company, ILOG, became acquired by IBM. At that time, we already had a lot of experience with our previous generation tools, I mean ILOG solver and scheduler, to apply constraint programming technology for solving real-life optimization problems of our customers, and in particular scheduling problems. But these tools were complex to use, and that's why we decided to develop a new tool, CP Optimizer, to make it easier to people with no particular background on artificial intelligence or constraint programming or operation research to solve complex scheduling problems. So CP Optimizer follow a model and run approach. The user focuses on providing a declarative model of the optimization problem using the classical ingredients of combinatorial optimization, I mean variables, constraints, expressions, objective functions. And the resolution is performed by an automated search algorithm so that the user do not have any resolution code to write. The search is an exact algorithm that can provide optimality proofs. It is deterministic. It means that solving twice the same problem will result in the same solution. It is usually anytime, in the sense that finding an initial feasible solution is in general fast. And it is continuous improving from version to version. So you will say there are existing optimization frameworks that work this way, like typically mixed integer linear programming or constraint programming tools. Yes, that's true, but from our point of view, these tools have some limitation when dealing with scheduling problems, in that they mostly deal with numerical decision variables, integer or floating point variables, whereas when you're dealing with scheduling problems, you are dealing with a particular dimension, that is the dimension of time. And in this context, there are some other mathematical concepts that naturally emerge, like, for instance, intervals to represent an interval of time and activity, for instance, or functions to represent the evolution of some quantity or state variable over time. You can also think of permutation of intervals that are dealing with unary resources, and also the notion of optional intervals if you're considering some events that may or may not occur in your schedule. So the idea of CP Optimizer is to integrate these simple mathematical concepts in the model, while keeping all the good ideas of other well-established optimization frameworks like mixed integer programming, for instance, in particular, the model and run approach, of course, the completeness of the search, some input-output format to understand and exchange the problem instances, the possibility to use your favorite programming language to define the model, be it C++, Python, Java, or OPL, if you know OPL. Also some tools to help developing models, like warning or explanation for infeasibilities of the model. Other tools, like the possibility to inject an existing solution as a starting point to the search, for instance. So let's see how a very classical academical scheduling problem can be formulated in CP Optimizer. I will take the example of the resource constraint project scheduling problem that you probably already know. The problem consists in scheduling a set of tasks with precedence constraint between the task and the resource requirements. Each task requires some quantity of cumulative resource that have a limited capacity, and the problem is to minimize the make span of the schedule. So here is the mathematical formulation of the problem in CP Optimizer. So as you can see, the model is using interval variables, AI, to represent the tasks, and it posts some precedence constraints and between the decision variables of the problem. It also creates a function that describes the evolution of the resource usage over time and posts a constraint on the maximum value of this function. Okay, so it is difficult to think of a more compact model. We can see the same model formulated in OPL and a solution for a particular instance of this problem. The OPL formulation is a one-to-one mapping of the mathematical formulation, and you can easily write the same model in Python, in Java, or in C++. Of course, I said that the main target of CPU optimizer are industrial scheduling problems, not academical ones. But nevertheless, CPU optimizer is very good at solving these classical scheduling problems. Some years ago, we published a paper summarizing some results where we closed and improved many classical instances of academical scheduling problems like RCPSP, job shop, etc. But I have to say that one of the reasons why we do not particularly focus on these instances is that they are usually small compared to the real industrial problems we face. For instance, the largest size of the problems of classical RCPSP is only 120 or 300 tasks. In real problem, we once had to solve a real RCPSP-like problem with 1 million of tasks. That was for an aircraft company in aircraft assembly. So most of the existing approaches developed for small problems won't scale to this size, whereas CPU optimizer can, and for this type of simple scheduling problem, it can produce solutions in almost linear time with respect to the problem size. But in the real world, scheduling problems are often much more complex than academical ones. In particular, you have complex activities and resources. Often there are different ways for executing an activity, for instance. Also, resources are complex machines, and they may process the activities by batches of limited capacities with setup times, things like that. The objective function is never as simple as a make span. Most of the time, several criterions need to be considered involving resource cost, tardiness cost, etc. Also, the problem are often over constraints. Not all activity can be executed, and part of the problem is to decide which subset of activities to execute. Also, decision variables are heterogeneous, and they evolve at the same time. The decision to perform or not some activity, decision on the start and time of the activities, the allocation of the resources, the grouping of activities into batches on some machine, etc. So it makes the problem complex. The problems are also very large, and quite often they require fast solving time. For instance, in the operational scheduling of a fabrication plant in the semiconductor industry, where we had a project, they had a rescheduling that occurs every 5 minutes, so the solving time cannot exceed 5 minutes, okay? So in general, the modeling concepts of CPU optimizer make it fairly easy to formulate those complex problems. For instance, there are the following things that are pretty easy to model. You can model variable activity durations. You can model oversubscribed problems that involve optional activities, hierarchical problems with a work breakdown structure, and alternative ways to perform some tasks in the hierarchy. You can also model different types of cumulative resources like inventory, reservoirs, activities that can be batched and processed together by a machine, by a resource, binary resources with second-dependent setup time and setup cost. So here is, for instance, a complete model in OPL of a pretty realistic problem in the context of semiconductor manufacturing. I will, of course, not enter into the detail of the problem, but it involves scheduling a certain number of lots. Each lot is composed of several steps that need to be allocated on the machine. Machine can group steps of the same family together into batches, okay? And it requires some setup time between batches. There are also some maximum waiting time between consecutive steps that must be satisfied as much as possible. And we have also a second optimization criteria, which is the total tardiness cost. So you see on the right side, the CPU optimizer model, and basically each component of the problem naturally maps into some modeling concept of CPU optimizer. So in CPU optimizer, we improve the automated search from version to version. On this plot, you can have an idea of the average speed of the different versions across a large number of different types of scheduling problems that we have in our benchmarks. And you can see that also the main ideas we introduce in the search algorithm that helps improving the performance. Some of these techniques are described in paper like failure-directed search or objective landscapes. So if you're curious to see what happens under the hood, most of it is described actually in papers. I will give the reference in the next slide. But let's say that our main philosophy is to consider everything that can be useful both in operation research or artificial intelligence, and to blend all this technique together into the engines. So if for memory, here is a list of papers about CPU optimizers that explain both the modeling concept, some example, and also inside what happens under the hood for solving the problems. And so here I'm done. Thanks for listening. I just want to add that the full version of CPU optimizer can be downloaded free of charge if you are an academic and if you use it for teaching and for research. So thank you for listening.